Hello everyone, my name is Micheal Lindemann and I'm here today to give a presentation on my paper called Igniting Precision, Amplifying Wildfire Prediction in Diverse Regions via Teacher-Student Model Fusion. This is a paper that I worked on while I was a student at the University of Alaska Anchorage, and this project was funded by the National Science Foundation. This paper was part of a larger project called Firewall, and Firewall stands for Foundations for Improving Resilience in the Energy Sector Against Wildfires on Alaskan Lands. The Firewall project as a whole aims to develop an all-inclusive, cohesive app or ecosystem where the different fire management folks can come together so that they can hopefully respond to wildfire events or, say, predict wildfire events in a more efficient and timely manner. So what are some of our motivations? Why do we want to be able to predict wildfires in Alaska? Well, this may not come as news to some of you, but Alaska has these fire-prone boreal forests, and we have extreme wildfire behavior in Alaska due to these boreal forests. These boreal forests tend to be right up against mountains. These mountains cause high winds, so when there's inevitably a lightning strike, it ends up lighting up these boreal forests like a tinderbox. And so it's not unheard of in the state of Alaska to have wildfires on the order of 500,000 acres or more. It's generally pretty common, actually. And so there also we have some more problems where we have all of these rural and remote communities. And so we don't have access necessarily to hospitals all the time. And so what ends up happening is people get sent home with home use medical devices. These are devices that rely on electricity to do something for them, say produce oxygen or at-home dialysis or something like that, right? And they all require electricity. And if a wildfire takes out electricity to the village, that's a major problem for these people with these home use medical devices, right? Another thing is these people rely on their freezers to essentially provide them food. A lot of these communities are not on the road system, so they can't just go down to Fred Meyer or wherever and go buy food, right? And so they essentially spend all summer hunting and fishing to fill up their freezers so that way they can make sure they have food to eat through the wintertime when there is none. And so you can imagine that, say in the fall, if there was a fire event that comes in and takes out the electricity for the village, and all of a sudden everybody's freezers start to warm up and all of their food spoils, they're going to have a major problem when winter kicks in about 3 months, right? So it's really of utmost importance to make sure that these communities can have consistent access to electricity. So some of the challenges that we face is Alaska is a very unique environment. So in the lower right-hand portion of this picture, there is actually a rainforest, right? And then in the upper portion of the image of Alaska there, that is an Arctic desert, believe it or not. And so we have a very broad scope that any model that wants to work over the whole state of Alaska needs to be able to operate over. It can't be specialized for just one region or anything like that. And so we have these very diverse vegetation types because it's such a broad state, right? Another challenge is that due to Alaska's high latitude, getting satellite data, and more importantly, consistent satellite data, can be very challenging. It almost exclusively limits us to satellites that are in a polar orbit, meaning they pass over the North Pole of the Earth, right? And so luckily, we do have these things called Landsat satellites, and they are in a polar, or at least a nearly polar orbit. And so their revisit time over the state is roughly once a week or once every week and a half, approximately. They end up covering the entire state. The issue with Landsat satellites is that their on-ground resolution is quite low. They've been around since the late 80s and early 90s. And so each pixel from a Landsat satellite is 30 meters. Its on-ground resolution is 30 meters. So their on-ground resolution is extremely low compared to what's available out there today from other satellite providers. The problem being that those other satellite providers are not typically in a polar orbit, so they cannot achieve imagery coverage over the entire state of Alaska. I went and I found a data set from Canada. And so this Canadian data set was actually put out by the Canadian government, and it was on Kaggle. I obtained the data set in 2023. And the data set was split into two different categories. You have no wildfire and you have wildfire images. The no wildfire images are strictly pictures of ground that has never had a wildfire on it, at least up until the point of this data set being produced. and put out there. The wildfire images are sort of split into two different categories. The first category is easy to see. It's in the middle there, where essentially you see there's a burn scar in that middle wildfire image. And so those are images where there has been a wildfire in the past. And then the image on the right is a good example of an image where there had not been a wildfire yet, but after the data set was, or after the image was produced, there was a wildfire, right? And so essentially this means we end up with two data sets that have wildfire images and we have no wildfire images. And we want to be able to split these. We want a machine learning model to be able to determine essentially what ground we think that there's going to be a wildfire on or has a higher wildfire likelihood, right? So there was around 43,000 images, which are plenty of images to train up a machine learning model. All of the images were 350 pixels by 350 pixels, and the on-ground resolution was not published with the data, but by comparing these images to what's out there and commercially available, we think that the on-ground resolution was somewhere between 1 and 5 meters. And so I want you guys to keep your eyes on those Canadian images there, and I'm going to bump down to the Alaskan data set, which I was able to produce. And so ready, and here we go. So you can see the difference between the Canadian data set and the Alaskan data set. So I produced this data set using essentially an Excel spreadsheet that's put out by the Alaska Interagency Coordination Center, which is continuously updated with fire data. This spreadsheet goes all the way back into like the 50s in Alaska. And I was able to produce 1,500 images total, 1,000 of which were wildfire and 439 were no wildfire. To make things as apples to apples for comparison as possible, I set them to 350 pixels by 350 pixels, just like the Canadian data set. So now if we do a principal component analysis or a PCA visualization, we can see why some of the existing models have struggled to do well on the Alaskan data, right? And so we see that the Canadian data is more spread out, right? Meaning that the models have an easier time discerning between the images. And the Alaskan data, by contrast, is all sort of clumped on top of each other, right? And so this means that really our models are going to struggle to differentiate between the no wildfire and wildfire images on the Alaskan side of things. So first we tried some widely used pre-trained models. So we tried BGG19, ResNet 50, MobileNet, EfficientNet B4, and EfficientNet B7. The accuracy varied between 50 and 60% on the Alaskan data and up to 80 to 96% on the Canadian data. Then we moved on and we tried training a logistic regression model on the Canadian data and then testing it on the Alaskan data. We saw about an 89% accuracy on the Canadian data and a 30% accuracy on the Alaskan data. We did the similar thing and we had the similar results with an MLP model, a multi-layer perceptron model. And then I started working on a bunch of custom CNNs. These custom CNNs were able to achieve an accuracy of up to 98% on the Canadian data. And the highest accuracy they were able to get on the Alaskan data, though, was about 75%. So here we can kind of see that custom CNN, which we will call custom CNN 1, it did very well in the Canadian data, right? 98.4% accurate with a F1 score of 97.81, which is great. When we apply that to the Alaskan data, we see that the accuracy was 75.6% and the F1 score was 70.19. And there at the bottom, you can see the different layers that I used to create this custom CNN. And again, this custom CNN had to be trained on the Canadian data because we simply don't have enough data for the state of Alaska to be able to train up its own dedicated machine learning model, right? So if we then go to the solution that we came up with to this problem, which was what's called the teacher-student model fusion, essentially, the way that I like to think of this is we train a model on the Canadian data set and we essentially give it some information. We allow it to learn a certain amount on the data set. And then that model then passes its traits down essentially to its children, right? And then those children are specialized with a trained wildfire specialist and a no wildfire specialist, right? Those guys are the specialized children. And then we do a model fusion, and that final model is sort of the grandchild model, right? And so I really like to think of this as sort of the grandparent and then the parents and then the child or the grandchild, right? And at the bottom you can see the layers that we ended up using for our models. And so here's the pseudocode for everything essentially that I just spoke about. So this essentially shows the exact same thing as what we were looking at in the previous slide, just in a more computer scientist level way. I'm going to kind of gloss over a lot of this, but essentially just know that we did basically the same thing that I was just talking about, where we created a no wildfire specialist and a wildfire specialist, and we combined them. So one interesting thing to point out here, though, is that the two models, so the two different wildfire and no wildfire specialists, have different results for their predictions. And so if they were different, we ended up using what's called a soft fusion, which is a probabilistic technique. And we used a posterior probability weight to combine with an alpha of 0.5. And so we could use different weights or optimization techniques to try to come up with the best weights, right? In order to fine tune our model. But we ended up actually determining that 0.5 was the best alpha to use here. And so if we look at some of the results from this, we can see that the teacher model with 2 students and a fusion ended up having an overall accuracy on the Alaskan data of 89% and an F1 score of 91.68. This is much better than the previous best that we had seen, which was 75.6%. And so one thing that I found really interesting here was that if we use the best CNN that I had developed as the teacher and the student models, right, it ended up having a lower accuracy on the Alaskan data than if we used the model that we ended up using. And essentially this goes back to what I was talking about earlier with the grandparents and then the parents and the grandchild, right? So the reason why it had a lower accuracy was actually because there was too much of the biases essentially that were making it all the way through to the final model. And so since there was too much biases in it, it had a lower accuracy. And so by leaving some things out so that way it didn't end up getting too biased towards the Canadian data, it ended up actually working better. And so if we look at the confusion matrix for this, we see that we did have a fair number of false negatives still. And so this is one thing that we would hope to improve with future iterations of this model, or hopefully maybe as we get more data for the state of Alaska. And so in conclusion, and for our future work, we really think the results of our study kind of highlight the effectiveness of our proposed model in improving wildfire prediction capabilities in challenging geographical locations like Alaska mainly. And then as far as future work, we want to move to multispectral. The Landsat satellites have multiple different imagery bands. For this particular model, we use the red, green, and blue bands, but there are a bunch more bands that we might be able to make use of. The next thing is we want to add a temporal aspect. So we want the model to be able to give us sort of an output of, we think that there will be a wildfire in this area in the next 2 weeks or next month or something like that, right? And finally, we want the model to run real-time and continuously over the entire state of Alaska. And it needs to do a couple of things to do that. So it needs to be able to bring in data automatically from USGS, process that data, and then run the model through over the data, right? And then it also needs to be able to sort of train itself as it goes. So it needs to train in an online fashion. So that way it's sort of more hands-off, right? It doesn't require as much human intervention. So that's all I have. Thank you guys very much, and there's my email. Feel free to shoot me an email with some questions.